Okay, in this second part of lecture 3, we will talk about some general and practical issues with regard to machine learning, basically about model selection and model evaluation. The lecture outline is we will first have a recap of linear regression and see the problem of overfitting, and talk about the one method to reduce overfitting called the regularization. Then we will take a simple Bayesian perspective of linear regression and then see the relationships between a maximum likelihood estimation and the sum squared error defined in the first part of this lecture. Then we talk about the mean variance trade-off and the famous method called cross-validation to reduce variance of the models. After that, we will talk about ROC analysis for model selection. ROC is short for receiver operating curve. And finally, a few words on the no-free lunch theory for model selection. Now first, a recap of linear regression and extend the linear regression to polynomial regression. So first, suppose we have n observations of a single variable x, which takes a scalar value. And for each xi, we have a corresponding target value, ti. So we have n observations paired with xi and ti. So we will return the input value in the typeface font, big X, which is a set of x values. And correspondingly, we will have a typeface symbol t, which is a set of corresponding target values. Now, suppose we have a number of data points. Here we have a number of 10 data points, which are sampled from a true distribution. And the green curve just shows this true distribution. Okay, we sample a number of x and the corresponding y's by adding some noise to the true distribution. Then this is a cosine function of x, which can be approximated by a polynomial expansion of the so-called radius functions of x in this way. And this is also called a Taylor's expansion. In calculus, we know that Taylor's expansion can approximate almost any function of x. And to formalize this equation, we will suppose that the target value t is a function of x and the corresponding feature vector w. And based on x, we will define a feature vector phi x. This is also called the radius function in some literature, especially in statistical machine learning. Now suppose here the feature vector phi x is comprised of the bias term, which is 1, and also the first order of x, then the second order of x, till the m order, x to the power of m. Now this Taylor expansion or polynomial is said to have an order of big M. And big M actually controls the complexity of this order, because with a larger M, we will have more more parameters to estimate. Now in the learning stage, we will find the best parameter vector W star to minimize error function. And in the last part of the lecture, we defined the so-called mean squared error, also called the sum of squares error in this way, which is the sum. Okay. So this is the sum of square error function, not the mean square error. This is the sum of square error function. So if we use the sum of squares error function. If we use the sum of square error function, it is measured by the sum of the square of the differences between the predicted value and the true target value. Now one problem remains. We need to choose the order of m. Obviously, if m is too small, then the approximation of the curve is not perfect. For example, here we show 4 figures corresponding to 4 different models with different order. For m 0 and m equals 1, the model represents 2 lines in the space. Obviously, they are not very good approximations of the green curve. And if we look at m equals 3, the red curve is our approximation. It looks much better. But if we further increase the order of polynomial to 9, the curve, the red curve, or our approximation, looks very strange. If we sample another data point from the cosine function, say a point here, then our estimation with m equals 3 is somewhere here, which is relatively close to the true value. However, using a more complex model like m equals 9, which is fitted by these 10 data points, the corresponding estimation is very far from the true value. So this is why we say if we do polynomial regression in this way, the model with M3 fits the data set much better than the model with M9. Now, in machine learning, our goal is to achieve good generalization to other data points outside the training set. Obviously, the model with m being 9 is not a model with good generalization. And to measure how good the generalization capability is, we can obtain some quantitative insights into the impact of the order of the polynomial m on the generalization performance by considering a separate test set. Then for each choice of m, we can then evaluate the error function for both the training and the test data set. And we can also see that, yes, we can see that in these 2 figures, the model with m being 9 does not generalize well and should have a larger value on the test data set. Now the question is how to quantify the error of a model on the test data set. And to do this, we will use root mean squared error, which is the sum of squared error divided by the number of samples, and after that take the square root of the mean squared error. And this is a very famous and widely used metric for measuring how good a model fits the data set in regression problem. Now, using this value, we will draw a plot of the model performances with respect to the order of m for both the training and the test data set. And we can see that for both the training and the test data sets, the performances decrease first, okay? And at a certain point, the performance on the test data set stabilizes. There's no obvious increase in the performance of the model with increasing m. But a more severe problem is at some point, say m equals 8, Even though the performance on the training set increases, the performance on the test set decreases drastically. This is a very significant signal of the model being overfitting the training set. So this means with our current polynomial regression model, we should stop here. We should not go beyond m equals 8. But actually, in machine learning practice, we will probably stop at m equals 3, because after 3, we will test a few other more complex models, but we do not see much improvement in the performance. So this means probably after m equals 3, the model performance saturates. So m equals 3 is a simple model which achieves at least as good performance as more complex models with larger m values. Now let's look at the cause of this drastic increase of error after m of 8. We can see that when we increase m, the magnitude of the parameters parameter values also increase, and the magnitude of the parameter value jumped to very large values at m equals 9. So these are very large feature values. So this is a signal of severe overfitting. Now, one way to reduce overfitting is by regularization. This is done by adding a so-called penalty term, or called a regularizer, basically defined in the length of the weight vector. So w to raised to the power of 2 is defines the length of the parameter vector. And in this way, we will suppress large weights because we also try to minimize the regularization term. Okay, we will try to minimize the contribution of the regularizer to this error function. And here lambda is a hyperparameter, and recall that hyperparameter is something we need to choose and test, but not learned from the training procedure. And we will also see that different lambda has different effectiveness in improving generalization. For example, if we take the logarithm of the lambda, we see if the logarithm of lambda is negative infinity, this means lambda equals 0, or no regularization at all. And if the log of lambda equals 0, this means lambda equals 1. Okay, but if log lambda equals minus 18, this means lambda equals e raised to the power minus 18, which is somewhere between 0 and 1. And it looks like that for a polynomial regression model, m equals 9. So this is a model. We fix m and we test the impact of lambda on performance. For this model, a large lambda, say lambda equals 1, better suppresses the error. And the last word is we can't directly optimize lambda. This is because if we take the partial derivative with respect to lambda, it is always a fixed value. So if we take the partial derivative with respect to lambda, it is always half of the length of the feature vector. So this is a constant, right? So obviously, if we look at this equation, if we want to minimize the error function with respect to lambda, okay, if we take lambda as 0, right? It always happens when lambda is set to 0. So we don't need to, we can't optimize the hyperparameter lambda directly using this error function. So recall that said in the first lecture, to choose the best value of lambda, we will use a so-called validation set, right? We will choose different model values for m and for lambda. They are called model complexity. So we will try different model complexities with different values for m and lambda using the validation set and find the best value of lambda using the validation error. Now let's take a probabilistic perspective of our polynomial regression problem. Recall that the goal of linear regression is to be able to make predictions for the target value t, right? So we will make some predictions of the target value t, given some new value of the input variable x, right? So we will use new value x to predict the value of t. Now we can express our uncertainty over the predicted value of the target t using a probability distribution in this way. This is a Gaussian distribution with the mean being the predicted value y of x given the estimated parameter feature parameter vector w, and beta raised to -1 is called precision. It is the inverse of the standard deviation of the distribution. Now, for this purpose, we should assume that given the value of x, say x0, we know the predicted value, or which is y of x0. And the Gaussian distribution is, for the target value t of 0, is a distribution around y of x0, like this way. Now the optimal situation is, of course, we can obtain a weight vector w. We can obtain a weight vector w. And given that weight vector, for each x0, t0 exactly matches y of x0. So this is exactly what this blue distribution illustrates. So this is a very good estimate of the parameter vector w. Now suppose we have another parameter w prime, and the distribution is looks like this one. Okay, obviously it does not centering around y of x0. Now this is not a very good estimator, right? So in principle, we want to optimize the parameter vector w so that the probability distribution of the target value t is a Gaussian distribution centering around the predicted value y of t, y of x0. At the same time, we also hope the Gaussian distribution is narrow, which means it focuses most probability density at y of x0. So generally, we will think a narrow distribution like this might be a better estimate, right? Because we focuses more probability density on the mean. Now, given the Gaussian distribution of the probability of the target value given the input x, we want to estimate the best vector W. So to do this, we will use the training dataset and calculate the log likelihood, the likelihood of our target values. And now assume that each data sample xi and ti is independent from other data samples xj and tj. So in this case, the probability of all the ti equals to the multiplication of the probabilities of each tn given the sample xn and the feature vector, which is this equation. Now we have the likelihood of the target values of our training data set defined in this multiplication of the probability of each target value given the corresponding input value x. Now we can use the maximum log likelihood estimation to estimate the best values of W. So we will take the logarithm of the likelihood. So the multiplication will be transformed to summation, and this probability for each target value will be transformed into this way. And we see that the last two terms are irrelevant, so they will not participate in the optimization of W. Then we will calculate the partial derivative of the log likelihood with respect to W, and then we will get an analytical solution for this estimate. So we will not go into the details, but the process of doing this is quite similar to what I showed in the gradient descent algorithm in the last part of the lecture. We have moved a step further to a Bayesian modeling of the problem. Okay, we take a probabilistic perspective of the linear regression problem by calculating the probability distribution of a target value t given the input x and the parameter w. After taking a probabilistic perspective as in the last slide, we are still making a point estimate of the parameter vector w, so this is not a fully Bayesian treatment of the problem. Then we will talk a slightly bit on a Bayesian approach for polynomial regression, but will not go into much detail. Recall that the training data are sampled from the real distribution by adding some noise, right? Then how does this noise come from? Let us make some assumptions about the weights, the parameter vector. We will assume a normal noise on the parameter vector, and this is a multidimensional Gaussian distribution of W with a zero mean and this covariance matrix. Now in full Bayesian, we have a maximum a posterior estimation of W. So we will estimate the posterior probability of W given the training data sample and the model parameters. Now by applying Bayesian rule, it is proportion to the likelihood times the prior. Actually, this is subject to a denormalization, which is the sum over all the possible values of W. So the denominator looks like, it is the sum of all the possible value of W, PTX W beta times P w prime given alpha. But this denominator is a constant. Right, so it is a constant to all the possible values of w, so it does not take any effect in optimization of the posterior. So usually we will not consider this denominator. So in this equation, this symbol means the posterior probability is in proportion to the right-hand side, which is the likelihood of the target values times the prior probability of the parameter vector. Now, let's take the negative logarithm of the posterior probability. By taking a negative logarithm, the right-hand side of the equation will be reduced to the two parts in this new equation. According to the equation of the likelihood of the target values, this part will be reduced to the first part of the new equation, and by taking the logarithm of the prior probability, the second term will become this. Now, if we look at the new equation by taking the negative logarithm, the first component is just the sums of squares error, and the second term is just the regularization term. And we'll make it more explicit by rewriting the second term to the length of the parameter vector raised to the power 2. So in this case, we know that the MAP estimate is obtained by maximizing the posterior of W, which is equivalent to minimizing the negative logarithm of the right-hand side of the posterior equation, and which is further equivalent to minimizing the sum of squares error subject to this regularization. So it is quite interesting because it establishes some link between a Bayesian approach of polynomial regression and the polynomial regression under the optimization perspective, as we shown at the beginning of this lecture. Now, with this equation, in the Fourier Bayesian approach, we should consistently apply the sum and the product rules of probability so that we can integrate over all possible values of W, as in this new equation. So to evaluate the predictive distribution P of t given x, we will integrate P of t over all the possible values of W. So in this integration equation, the first part, P of t, is given in the last slide, and we omit the dependence of P of t on the model parameters of alpha and beta to simplify the notation. And for the second term, this is just the posterior probability of P of W given in the equation above.